welcome you all to this course on defects in material. Okay. In the last class, we talked about the basic concept of dislocation. Let us just do a recap of what the essential features of the dislocation which we have talked about it before we go further. Okay. The first thing which we talked about it is what is the need for having a dislocation. That stemmed from the fact that when the people were trying to find out stress which is necessary to deform a material, it was observed that the stress is much lower than what the theoretical fracture strength. Then the other factor is that when people were looking at the crystal growth, then it was observed that the growth of the crystals are much faster than what is dictated by the general theory. Then they thought that there may be some defect which is responsible for it. Similarly, when X-ray diffraction peaks from single crystals were looked at it, the intensity of the peaks were found to be much higher than what is expected if the sample were perfectly flat and did not contain any defects. So these features necessitated for putting forward the concept that the defect is present, okay, which is a one-dimensional line defect. Okay. We looked at it, what is the type of this line defect. There are two types of line defects which we can think of. One is called as a screw dislocation and another is called as an edge dislocation. Then we also mentioned that these dislocations have some features. How do we characterize these dislocations, or what are the properties which we should look at to tell that this is an edge or a screw dislocation. To do that, we should know what is the line direction, what is the Burgess vector of this dislocation. We looked at it how to define the Burgess vector of the dislocation, what is the convention which is being followed. Okay. Essentially, to find out the Burgess vector of the dislocation, what we should do it is that first we do Burgess circuit around it, that is starting from one point, complete a path, okay, coming back to the starting point, okay, keeping the defect within that circuit, okay, and then do the same process around a region which we call it as an ideal crystal which does not contain any defect in it. Then one will find that there is when we reach the end point, there is a gap between the starting point and the end point, and the separation between them defines this Burgess vector. Okay. And in this particular specific case, the line direction of the dislocation is taken to be the one which is looking into the screen. Okay. That is called as the sense of this dislocation. This particular diagram which is being given is for a simple cubic lattice. Okay. We will talk about dislocations in other lattices in the later class. Okay. Then I also mentioned that what are the other ways in which the Burgess vector could be defined and why it is important that this is the only method which has to be used. Okay. Then about Burgess circuit around a screw dislocation. Okay. Then another type of a dislocation which we considered are the Frank dislocation or the Frank loop. This essentially is that if we remove one of the layers partly, not completely, like we assume that the part of the layer has been removed. Okay. Sample. So we are only showing a cross section of the sample. Now one can immediately make out that from between this region and this region there is an extra plane which has come, and this is exactly similar to an edge dislocation, right. So, but in this case the Burgess vector of the dislocation, this is the plane of the defect, this is the plane of the defect, and this Burgess vector is essentially perpendicular to the plane of this defect. Okay. Then we talked about a shear loop, and most of the time the dislocation need not be a perfect screw or an edge configuration, it can always, most of the time, it is going to be a mixed type of a dislocation. That is, the dislocation can have, that is, if the dislocation is like this and the tangent to the dislocation gives the line direction, suppose I denote it by u, and the Burgess vector is inclined with respect to the dislocation. Okay. These type of dislocations are called as mixed dislocations. Mixed dislocation can be thought of as combination of a small screw and an edge segment together. That is, if I take a component of this, if this is the angle theta between them, okay, I can find a component of this dislocation in this direction, which I will denote it as Bs, okay, and the component which is perpendicular to this, which I will denote it as Be. So, Be is nothing but the edge component of the dislocation, and Bs is nothing but the screw component of this dislocation. Okay. That way also we can define a mixed dislocation. In these equations, what has essentially been given is that using vector notation, how to find out the Burgess vector of the screw and the edge component. So, the type of dislocations which we can think of is either edge or pure screw, or a mixed dislocation, which is a mixture of both screw and edge component together, okay, or a Frank loop. These are all the type of dislocations which we can have as perfect dislocations. There is another type of dislocation which is there, is called as a partial dislocation, which we will talk about it later, much later. Okay. Having talked about perfect dislocations, let us look at the moment of dislocations. Okay. Because we know that the dislocations are responsible for bringing about shape deformation to the materials or plastic deformation of the material. That means that plastic deformation is a permanent deformation of the material. That means that the material has flowed, okay, from one region to another, and this is associated with the moment of dislocations. Okay. What are the type of, how exactly this moment of dislocation brings about the shape change? Let us look at it. Let us take the example of an edge dislocation. In the case of an edge dislocation, here essentially a cross section for a simple cubic lattice is being shown, that is cut section of a cubic lattice is being shown, okay, by applying a shear stress, okay, essentially this dashed line shows essentially the slip plane. The extra half plane is lying, extra plane is lying above this slip plane, and below this slip plane is the normal lattice. If we look at either of this region, the above the slip plane as well as below the slip plane, the lattice seems to be perfect. Only difference is that between these two layers, one extra half plane has come. Okay. This is how we define a edge dislocation. Suppose we apply shear stress, then what is going to happen is that under the action of this stress, okay, the atom that numbered 1 here essentially is that since the stress is being applied in this direction, this is moved a little bit, and when the 2 is moved a little bit, it becomes closer to 1 and it makes a bond with it, and when such a bond is being formed, the layer becomes like this, and now this layer 3 has now become the extra plane. By doing a process like this, we can see that essentially at the end of it, the dislocation has come out of the sample surface. When the dislocation has just come out of the sample surface, it is perfect lattice we see in between, but with a step on either side of it. Okay. So, this step is essentially is what it gives rise to the shape deformation. Suppose we assume that we have a solid block in which, that is, I will just show a two dimensional analog of it. Okay. Suppose we have dislocations which are present in this sample like this. This is one with an edge dislocation with a bias vector which is positive, another with a bias vector which is negative. Okay. And this is the slip plane. Okay. When the dislocations are within the sample and when they are moved partly, suppose we assume that this dislocation, let us assume that the dislocation is lying here, and from here it has moved a distance and reached here. Actually the dislocation has done some work, it has shifted some plane, but shape deformation has not taken place. When does the shape deformation takes place? When the dislocation completely comes out of the sample surface. Okay. Like the way we have considered it, what will happen is that in this case the dislocation will come out. Okay. And in this specific case the dislocation comes out like this. So now we have from an original shape which is there, the shape has average shape has changed. So that means that shape change has taken place. So when the dislocation comes out of the sample surface, it generates step, and the magnitude of the step which it creates is of the order of is the same as the bias vector. Okay. This is what is being shown for a screw dislocation. What is the direction in which this step has been created? In both the cases, it is in the same direction as the bias vector and in the slip plane. Let us look at what happens in the case of a screw dislocation. In the case of a screw dislocation, okay, as the dislocation moves in this particular direction, a step is created in this direction. The movement of the dislocation and the step which is being created are perpendicular to each other. Okay. So that is what essentially is being shown in this specific case, in the case of a cube where a screw dislocation is moving. As the screw dislocation moves, it finally generates a step which is, okay, this is the line direction, okay, and the dislocation moves in this direction. As the dislocation moves, it creates a step, and when it comes out of it, you find that on either side a step has been created. Okay. Let us look at the case of a slip which will be produced by motion of a prismatic dislocation loop, okay, or the Frank loop which we have just mentioned. In the case of a Frank loop, as you can see, the bias vector is all going to be in this specific direction. That is, it is perpendicular to the plane of the loop. Okay. Since bias vector is perpendicular to a plane of the loop, as we know in the last class we defined that is defined by u cross b, where u is the line direction and b is the bias vector of the dislocation. Okay. So the plane which contains, or the slip plane which contains, which is perpendicular to the line direction as well as the bias vector, is essentially the this particular plane, okay, and which is perpendicular to the plane in which the loop is lying. So the loop has to move up or down, and finally it will come out of it creating a step. This is what essentially will happen. In the case of motion of a shear loop is a, how can we visualize what is a shear loop? Essentially, if we take a dislocation which is in a plane, you have the same plane, we have a dislocation which has a bias vector which is in this direction, and another where the bias vector is negative and this is positive. We assume that this is in a particular plane. Okay. Because one of the property of the dislocation is that the dislocation can never end within a material. First one should understand this concept. How one can understand this? Suppose we assume that there is an extra plane which is going to be there. Sample, I will just this is the slip plane, this is the extra plane. The extra plane is completely there up to the end. Okay. Suppose we take a perfect crystal which has got only this much number of lattice planes which are there and join it to this surface. That is equivalent to making this dislocation line which goes like this, okay, end. That is, suppose I put another slab of it here which is a perfect crystal, that is equivalent to the dislocation line ending at this point. When this happens, this is, if you look in this particular direction, essentially it is equivalent to putting an extra half plane in this direction as well as in this direction and another extra half plane. That means that this also, in this direction also there is an edge dislocation, this direction is also an edge dislocation, and they are joined together at this point, and the dislocation has come out of the sample surface here and out of the sample surface at the other side. That means that the dislocation can never end within a material. Okay. The dislocation can end either at the grain boundaries, okay, or at free surfaces. So, if a dislocation cannot end within a material, okay, the two options which it has, either it can come out of the sample surface or it can form a loop, so that it is we can say that it does not neither begin nor we cannot define where it starts and where it ends, because it is by forming a loop, okay, we can make a dislocation which satisfies the condition that the loop does not neither begin nor end within the material. Okay. In this specific case, okay, if such a loop is being formed, okay, and when the line direction remains, like I can assume that this is the loop which is being formed, and one part of it, you assume that this part of it is on the behind the screen, and this part is above this or in front of this board, okay, and we have only shown a cross section. And as we have mentioned always, that the as I mentioned earlier, the line direction of the dislocation, okay, has to be, some particular sense has to be chosen, and the line direction cannot just like that change, it has to follow the same line direction. So, if the line direction remains that same, okay, if you try to construct a Budge circuit around a dislocation, we will find that the same way we will be defining it, but we find that with respect to a coordinate system which we have chosen, this side it has become a negative value for the same sense of the, because here the sense is going to be the dislocation line coming out of the screen, and here the sense of dislocation is going to be going into the screen. Okay. So, when this sort of a dislocation loop forms, okay, if the Budge vector is in a specific direction, then with respect to the line direction, okay, here the line direction and Budge vector are perpendicular to each other. Here the line direction and the Budge vector are in the same direction, and in between regions the Budge vector is inclined with respect to a line direction. So, for a shear loop, okay, some region will exhibit pure screw type of a dislocation, some regions exhibit edge, pure edge component, and in between regions will exhibit both screw and edge components. Okay. In this, to this dislocation, if we apply a shear stress and try to deform it, okay, suppose we assume that the stress is applied in this particular direction. As we know that the edge component will be propagating, the positive one in this direction, negative one is in this direction. When they propagate like that, finally they will be coming out of the sample surface and creating an edge. Okay. But the screw component, if we consider it, okay, this is the line direction, or this is the line direction, and Budge's vector is also in this direction. So when this dislocation also moves, as the dislocation moves in this direction, the step which is going to created is the same direction as the one which the Budge's vector has created, as it is being shown here. So finally what is going to happen is that when a shear loop comes out of a sample surface, step is created only in one direction. Okay. This I will give it as an assignment. When you try to solve it, you will understand clearly how the shear loop, what sort of steps are created on the sample surface when the shear loop comes out of the sample surface. Okay. Another thing which one should understand is conservative and non-conservative moment of dislocation. The cases which so far we have considered, everywhere when the dislocation moves in the slip plane, okay, both the screw and the edge dislocation, and as it comes out of the sample surface, okay, the volume is being conserved. Okay. When the volume is being conserved, this sort of moment of dislocation is called as a conservative moment of dislocation. Okay. If a like for example, if an edge dislocation, you consider this specific case, this dislocation moves perpendicular to the slip plane. If it moves perpendicular to a slip plane, some row of atoms should be removed from this region and it should be brought to somewhere on the surface. So when that has been brought onto the surface, in that process what we have created is that the dislocation has moved, but if you look at what is the volume which has happened, the volume has increased. So anything which involves increase in volume, okay, it is called as a non-conservative motion of movement of dislocation. And the best example of non-conservative movement is climb of dislocation. Okay. Another important aspect which one has to think about it is that in most of the material, or as I had shown in some of the example earlier in the last class, you might have noticed that many dislocations are at many places, they are splitting into different type of to various components. Okay. In this particular case, what is the rule which is governing the Budge's vector of the different components of this dislocation? This is one important aspect one should know. To understand this, what we have done it is, we have taken a dislocation, okay, with a Budge's vector B1. Okay. This has split into two dislocations with Budge's vector B2 and one another with Budge's vector B3. You should notice carefully that the line direction here in this direction, okay, is it the same line direction which it follows, okay, with respect to a dislocation. So that means that if this is the line direction of the dislocation, this will have a line direction. Everywhere the line direction may be, line direction is defined by tangent to a dislocation, but the sense of the direction remains the same, okay, at all places. Suppose we form a Budge circuit around this dislocation, okay, that is how we, around the line direction, we create a Budge circuit, and then a region which is adjacent to it which does not contain the dislocation, we put the Budge circuit, and then we can find out what is the Budge's vector of the dislocation. That way if we do it, we can find out what is going to be the Budge's vector, and it is given as B1. In this region which contains the dislocation which has split, okay, you take a Budge circuit encompassing both the dislocations together. Okay. If we do the budget circuit around these two dislocations also, okay, encompassing both of them, then the budget vector which we will be getting it, okay, since it's the same, so the dislocation has just gone through this, the budget vector here, okay, since it is in the region which encompasses both the dislocations, this should have a budget vector because the material continuity has to be maintained. This B1 should be equal to, okay, whatever the value is, that the B2 plus B3 should also, when we do a budget circuit, whatever is the budget vector which we get it, should be equal to magnitude wise, it should be equal to that of B1. Okay. If we take the sum of all these budget vectors, B1 plus B2 plus B3 should be equal to 0. That means that if the budget vector is in this direction B1, if the budget vector B2 is in this direction for this dislocation, the B3 budget vector will be in this direction, such that at this junction if you see, the B1 plus B2 plus B3 will be equal to 0. This is similar to the electric current flow. We see that which we call it as the Kirchhoff's law. Okay. If different resistance we connect together, the current flows in a particular direction. At a specific point, if we try to find out when they are joined together, the sum of the current should be equal to 0 at that point. Okay. This part of it, as I have mentioned earlier, the glide plane is defined for a dislocation, okay, by taking U cross B. For an H dislocation, the glide plane is specifically defined, okay, because if this is how we look at it. Yeah, one should also remember about what is the symbol which is being used to represent the dislocation. Generally, the symbol which is being used to represent the dislocation is just this perpendicular line. Okay. This represents general dislocation. Okay. It does not distinguish between whether it is a screw dislocation or an edge dislocation. But if you look in the book of Hurth and Lothe on theory of dislocations, there the edge dislocation is defined by a symbol which is being put like this, an inverted T. That is, this direction which points is where the extra plane is there. Okay. If the extra plane is up, this is the way it will be shown. This is for essentially an edge dislocation, the symbol which is being used. Okay. Using that symbol, if you try to draw, this is the line direction U and the budget vector is in this direction B. Okay. If you take U cross B, which is equal to nothing but modulus of U into modulus of B into sin theta, okay, the angle between them, correct. This is going to define an area, okay, and the vector is perpendicular to it, that represents the plane normal. So this plane is called as the slip plane for the case of an edge dislocation. In the case of a screw dislocation, okay, if you take the cross product, this is going to be 0 because the U as well as the B are going to be in the same direction. Okay. That means that in this specific case, the dislocation, if we no slip plane is defined, that means that any plane which contains this dislocation line is a potential slip plane. Okay. The dislocation can move on any of this plane. Then what dictates on which plane this screw dislocation will move? The answer is, it is decided by, okay, the plane which has got the least frictional resistance to the movement of the dislocation. In the case of FCC material, one plane has got the least frictional resistance to moment of the dislocation, okay. And especially for FCC material, for a perfect dislocation, two slip planes intersect each other for the same dislocation, okay. Maybe this is one plane and there is going to be another plane which may be inclined with respect to it. These two planes in which the same dislocation can move. Suppose depending upon the direction in which the applied stress has been direction in which the external stress is applied, okay. Take the component of that in the slip direction, slip plane, okay. Whichever one has got the higher maximum resolved shear stress, that is the plane in which the dislocation will move. Suppose it meets an obstacle at somewhere when it is being moving in this slip plane, then it has always that option to move in the other slip plane also, because the slip plane is never defined. Only condition essentially is that all the planes which contains the line direction of the dislocation is potentially a slip plane for screw dislocation, but on which plane it will move or which plane will act as the slip plane is decided by the plane which has got the least frictional resistance, okay. This I had already explained to you that the dislocation line does not terminate within a crystal, okay. Why it should be so? Now one more thing which I will talk about it is, I mentioned about the frictional stress, correct, okay. How do you define a frictional stress, okay? We talked about the theoretical strength which is required in the case of a material which just does not contain any dislocation, okay, in the last class, okay. Now let us look at the case of the same material where it contains an edge dislocation, okay. In this, if you look at it, this figure, okay, the atoms which are represented with open circles, that represents a perfect lattice, okay. Into this lattice, okay, and this is the slip plane, okay. Across the slip plane, now we have added an additional atom at this particular position in between these two layers. When one extra layer has been added, to add this extra layer, the other layers will be pushed on either side. So that is what is being shown, is that now this atom is being pushed from here to here, this atom is being pushed from here to here, then this atom is being pushed from here to here. So essentially the atoms which are originally in this position, by adding just an extra layer, okay, the atoms are displaced from their original position to a new position. As we go further away and away, we find that this displacement gets reduced on either side, okay. This is the same thing can be viewed by two different ways. Suppose I take that when I go very further away and choose that as the coordinate axis, then I will notice it that these atom positions will be just identical to each other, that is the original position as well as the atom which is displaced, okay. From starting from that point, okay, if we try to measure what is going to be the displacement which is going to take place, we will see that the displacement is increasing, okay. Like here, this atom is with respect to this is the position, with respect to it, this is the position, with respect to it, this is the position, here to here. So you can see that the B is continuously increasing it. That is what essentially is being plotted here, how the displacement is changing, and as we go further away, the displacement remains the same. This is just the displacement which we have plotted it. For the present, you don't bother about this particular figure, which we will come to it much later, okay. This is regarding a dislocation which is dissociated into partials, okay. This is a case which corresponds to in the case of a metal, and this is one which corresponds to in the case of a non-metallic material like covalent or ionic bonded material. Okay. Let us first consider only this case of a metallic sample. Okay. In this case, this is what is being plotted is a derivative of this is being plotted. What is the derivative of displacement with respect to a distance? This you know that dx equals nothing but a strain, correct? So from this you can make out that beyond a particular distance, though displacement is going to be there, with respect to origin, that strain, if you try to calculate it, that will turn out to be 0. The maximum strain is going to be there at the center, correct? So that is what essentially it is being shown. But if you see how the displacement is taking place, it is a very gradual one. So if you look at the slope of this, okay, then over a large number of planes which are further away from the dislocation line or the core of the dislocation, okay, the displacement is taking place. This is what it happens in the case of a metallic system. What is the difference between a metallic sample and a ionic or covalent bonded sample? In the case of ionic or covalent bonded sample, the charge neutrality has to be maintained. Okay, otherwise there is a space charge effect will come. Because of this, all the displacements which are being taking place is essentially taking place over a very small region of the sample. That means that all the change in displacement of the atoms when an extra plane has been added is confined to a very narrow region. Okay. So if you try to see, if you try to take a derivative of this is the way the sharply the displacement or the strain will be occurring within this region close to the core of the dislocation. Okay. If you try to calculate what will be the stress which will be corresponding to this, okay, then one can immediately get an expression of this type. The derivation part of it, I am just omitting it. Okay. Essentially this the stress depends upon the shear modulus, Poisson's ratio, okay, in the 1 minus nu the Poisson's ratio. And another important factor it comes is that all this region over which the strain is taking place is confined to very small region. Okay. So essentially one more term comes which is essentially called as the exponential of minus 2 pi w by b, where w is defined as the width of the dislocation core or the region over which most of this strain is taking place. Okay. Because this is a highly strained region, okay, there will be a stress which is corresponding to it. If we apply a stress, okay, that stress has to overcome the internal stress to make the dislocation move. So in this specific case, the internal stress which it has to overcome is going to be very high, and in this particular case the internal stress which has to be overcome is going to be very small. Okay. To understand this better, okay, I had given a comparison between the theoretical stress which is required for deforming a material in the absence of a dislocation and one when deforming the same material when dislocations are present. As we have mentioned earlier, in the case of a material where no dislocation is present, like an example the whiskers where only point defects are there, no dislocations are there, okay, and one layer of an atom, okay, the next layer of an atom has to be, all the layer has to be completely moved. So what is the area, and that gives the total frictional stress. These atoms have to move from here to this position, So all the atoms will be shifted correspondingly, then it will be moving from here to this position. So this is the maximum theoretical stress which is required, and that is given by this formula. The tau is equal to mu b by 2 pi a into sine. In fact, this expression should, it's not the, it should be 2 pi x by b, okay. The pi is missing in this expression, okay. Let us consider how this expression gets modified in the case of a material which contains a dislocation. If you notice here, all atoms have to be displaced, okay, to bring about, that is every atom has to be displaced by a Burgers vector, okay, to bring about the displacement. Let us see what happens in the case of material which contains a dislocation. So we are revisiting what we have talked about some time back. If you look here, okay, when we apply a stress, okay, shear stress like this in this direction, and this is in the negative direction we are applying it. Essentially, under the application of this stress, the atoms on the lower half, especially this one, will be, if it is shifted a little bit, now it is much more closer to the atom which is going to be close to 2. So a bond is being formed, okay. And when this bond is being formed like this, the bond is being broken here. Now if you see it, this is what it has happened, is that this has become the extra layer. Initially the extra layer was here. What have we done? Only the bonds are being broken and joined, bonds are being broken and joined. When this sort of a process is occurring, okay, it appears as if the extra layer which was here has shifted to this position, it has shifted to this position. When finally this bond is broken and it is joined here, that extra layer has just come out of the sample surface. So what have we done essentially? We have not moved any of these atom layers. By application of this, a small displacement which has been created successively to either the top or both the top and the bottom layer in different directions, okay, only at regions which is very close to the dislocation core, okay. That way we are able to make the dislocation move. So that means that the stress is doing, the applied stress is doing work only in a very small region of this material, and as I had shown in the last slide, the stress which is required is, this is the value of the stress. If we substitute the values, okay, because here mu what is being called is nothing but g, okay, it is the same value. B is the Burgers vector of the dislocation in this case. Here x is essentially going to be the small distance which it is being displaced. In this specific case, this is going to be w is the width of the dislocation core. If these values are substituted, one will find that the lattice friction stress which is occurring in the material, okay, is maybe 10 to the power of minus 4 to 10 to the power of minus 5 order smaller than that of the theoretical stress which is necessary for making one layer to move on top of the theoretical shear strength, okay. From this it is very clear that when a dislocation is moving, okay, very small stress is necessary to move the material, okay. This one can understand with another example which is a practical example. For example, if you see in this floor, there is a carpet which has been put, okay. Suppose I wanted to move the carpet by a small distance, maybe about something like 2 inches. What is the option which I have? Or for example, if I wanted to move this, what I have to do it is I hold that end, both these ends, just try to pull it. When I try to pull it, the entire layer has to be shifted by the same amount, okay. The area over which the frictional stress has to be overcome becomes extremely large, correct. What is the other option which we have, with which, or a smart way in which we can move this carpet? Because the carpet is very heavy, lifting it and moving it is going to be difficult. Another way in which we can do it is, we can introduce a rod into this carpet. Okay. If we introduce a rod beneath it and just roll the rod from one end to the other end, okay. As the rod rolls out and comes out of the sample surface, we find that the carpet has moved by the same distance. So, moving of that rod requires extremely small force. Okay. So, this is a very clear indication that all other regions, if we try to look at it, it's lifting the carpet a little bit, and as the rod rolls, okay, the carpet is the other region, it is brought back to the same position, but a shift has been introduced. This way we will find that at the end of it, when the rod comes out of the sample surface, the carpet has been shifted by the distance which we want it to be moved. Okay. This is exactly that same way in which a dislocation also moves within that sample, or the dislocation imparts plasticity to the material. So, every time a dislocation moves and comes out of the sample surface, it has given a displacement of atoms by the bias vector, and when it comes out of it, a step, like as I had mentioned here, the step of the order of a bias vector has been created, okay, on the sample surface. Okay. So, essentially what we have considered so far is what is the need for a dislocation, how an edge and a screw dislocation can be defined, okay, or how are they defined, edge and screw dislocation. Then the bias vector of the dislocation, line direction of the dislocation. Once the line direction and the bias vector has been defined, okay, how from that we can get information about the slip plane, okay, or a glide plane. Okay, there are some subtle differences in some books they make between slip plane and a glide plane. The glide plane is called as the plane in which only a single dislocation when it is moving, especially in this specific case itself, if we consider it, this plane in which only a single dislocation moves, this will be called as a glide plane. And when more dislocations are moving in this plane, the terminology which is used as a slip plane. In many other books you will find that irrespective of whether it is one or this one, the same it is being used as a slip plane itself. Okay. But one should understand that it is only the number of dislocations which are used to define whether it is a glide plane or a slip plane, but it is the plane in which the dislocation moves. Okay. That is the thing which you should understand. Then the next question is that how to define the bias vector. Then we looked at it that if the dislocation, many dislocations come and join together, that is, we mentioned that the dislocation can neither begin nor end within a material, correct. So, the consequence of that is that if a dislocation is present in a sample, there is another dislocation which is being present there. Okay. The only way in which these dislocations can present that, since they cannot end there, they have to join together at some point, that may be, so there will be many junctions which will be created, okay, or yes, single dislocation itself can come out only it is present, then it cannot end within the material. So, the dislocation line from one end to the other end, either it should be from one boundary to the other boundary in a polycrystalline material, or if it is a single crystal material, from one surface to other surface, the dislocation line should go. Okay. And many dislocations are there. We will find that if the dislocation gets terminated, if it has to terminate, another dislocation will be originating from this point. So, these sort of junctions will be formed. Okay. What is the condition for these junctions to be formed? Okay. That is the bias vector, if we take it, the sum of the bias vectors has to be equal to 0. Okay. That is a condition which it has to satisfy. And then we looked at what is the theoretical stress which is necessary, okay, for a material which contains a dislocation, okay, if it has to make the material deform. Okay. So far we have mentioned about the different type of dislocations, and we have talked just in simple terms, okay, moment of dislocations. Okay. Before we talk about interaction of dislocation, the next thing which we should know, we have to understand is about that what are the stress and strain fields around a dislocation. Because in this talk itself you have noticed that around a dislocation there is displacements which are taking place. Whenever there is a displacement which is occurring around a dislocation, it will generate strains, and corresponding to that strain, using the generalized Hooke's law, we can find out what is the stress which it will be generated. Okay. If you take the product of stress and strain, okay, then that will give rise to an energy which is increase or decrease in energy which is going to take place within the material. Okay. All these things we will how to calculate it, we will be discuss in the next few classes. Okay. We will stop here now.